There are two major approaches to AI. One is called Symbolic AI, or also known as good old-fashioned AI, and the other is called machine learning. Both can be used to solve problems, and I will show you the differences by programming a robot. And this robot has the task to rescue a space station.
Okay, we are on a space mission and a machine caught fire. The only option that we have is to throw the machine out the door. But unfortunately, the job is too dangerous for an astronaut. The only option is to use a robot to get the block out.
By the way, if you enjoyed this video, please consider subscribing to my channel, then you will not miss one of my future adventures. There are different options to get the job done. The first is you can remote control the robot. For instance, you are in a control room and from there you remote control the robot to move the burning machine out of the door. The other option is to enable the robot to autonomously solve the problem. And AI offers two approaches for that. The first one is to explicitly tell the robot what to do in which situation. And the other one is to let the robot figure out on its own what's the best approach for solving the problem.
The first option is straightforward. You equip the robot with a camera and remotely control the movement, forward, backward, and turning left and right. You have to get behind the burning machine block to push it out the door.
In this case, the robot is just a mechanical tool in our hands. All the thinking and decision-making happens in our brains, and there's no intelligence in the robot. And for us, it's not a real challenge. We take one look at the scene and we know what to do. Now we want to automate the process so that the robot can act on its own. And the most direct way is to try to formalize our thinking process. That means we formulate rules and put it into an algorithm that the robot can follow. This approach to AI is called Symbolic AI, also known as expert system, or in the meantime it's called good old-fashioned AI. And the idea is to capture our knowledge and put it into code, so that in this case the robot will perform the task that we would perform if we would remotely control the robot.
Before the robot takes action, he first has to analyze the environment to figure out where the walls are, the machine or the door. In our case, the robot is able to detect objects in the environment through a kind of radar system. The robot sets out rays in different directions, and if hitting an object, it gets back the information what kind of object it was.
I'm not going deeper into this because it's beyond the point I'm trying to make. We simply assume that the robot has all the information about the environment to take a meaningful decision about the next movement. The essential part is to tell the robot how to get the burning machine out the door. So we need to develop a strategy for the robot that will reliably work in most of the cases.
Maybe the best approach is to move the block to the middle of the doorway so that the robot can then push it straight out the door. And this is how we would define the waypoints of the robot in our case.
So in our algorithm, we would encode how to find the waypoint depending on where the robot is, the block, and the door.
And this is how it looks like in action. The robot moves to the side of the block, pushes it into the middle of the doorway, gets behind it, and pushes it out the door.
In game development, this is a common understanding of the term AI. Game developers program the behavior of enemies or non-playable characters in this way, and the great advantage of this approach is that at each moment you exactly know what the robot is going to do because it follows the rule we have given him. The clear disadvantage of this approach is that it becomes pretty ugly in more complex environments. And besides the walls, we have no other obstacles in our room, which isn't very realistic.
But even here, we can't tell the robot what to do if the block is positioned directly at one of the walls, at least for robots that are not able to lift and carry things.
The second approach is called machine learning, and it means that the robot learns on its own how to solve the problem. But it also means that we have to train the robot before we can put it into use. As before, the robot can observe the environment, so at any given time the robot has all the information about the objects in the scene. But now the robot has to decide on its own what's the best move to get the block closer to the door. So we need a mechanism that takes the observation from the environment and returns a decision which movement to make. And this mechanism is called a neural net. It's a fancy term, but you can think of it as a clever way to store the decisions based on each constellation. And a neural net can be trained so that if the robot finds a better way to solve the problem, the neural net is adapted accordingly and returns the better decision. Learning in this case has a clearly defined meaning. The more often the robot tries to solve the problem, the better he gets. That also means we need to tell the robot whether a decision was good or bad. And for this we are using a method called reinforcement learning.
But how does the robot learn which the best decision is? Very simple, by try and error. At the beginning it's just a brute force approach. The robot takes a series of random decisions, thousands or millions of times, until by accident a series of right decision appears that leads the robot to push the block through the door. At that moment, the robot gets the reward so that the system learns that this choice of decision was better than the others, and the neural net is adapted accordingly.
Over time the decisions get better and better, and at some time the system is good enough that wherever the block and the robot are initially in the room, the robot will be able to move the block out of the door. Then we are able to deploy the robot in our live environment to rescue our space station.
The clear advantage of this approach is that it also works in more complex environments, so we can place obstacles in the room and the robot will still learn how to get the block out the door.
But there are at least two major disadvantages of this approach. First of all, the training process is pretty inefficient because basically the system has to figure out all the ways that don't work. In the meantime, there are some approaches to mitigate this, but still, if the environment changes significantly, you have to train the robot from scratch. The second problem is that a neural net cannot be debugged, so if it takes a wrong decision, we cannot figure out why. The only option is to keep on training until it makes better decisions. Both approaches in AI suffer from one major drawback compared to the human mind. They lack the flexibility to adapt to situations previously unseen. AI systems perform well in highly specific and specialized situations, but fail outside their clearly delineated domain. And this is why progress in self-driving cars is slower than many people hope. Because in the real world, so many unforeseen things can happen, and you just don't want to sit in a car that's not prepared for that. So these are the fundamental approaches in AI, and any solution implementing AI technologies use either of them or a combination. But for sure, the detailed methods depend on the problem that you try to solve.